Okay, I will assume that you have taken the time now to work these problems, and we will go ahead and go through these solutions. So, first determine the specific heat of a metal if 100 grams of the metal cooling 50 degrees Celsius gives off 500 joules of heat. So as we read these, it's especially important that we start labeling things as we read. Determine the specific heat. Find the specific heat. S equals what? Of a metal if 100 grams, that's my mass, of a metal cooling 50 degrees Celsius. So this isn't an initial or final temperature, it cools by this amount. So that is actually already delta T. And it says that it gives off 500 joules of heat. That's my Q. So another thing to note in this case, though, is the directionality of the delta T and the Q. If the metal cools, it's not going to be gaining temperature, it's going to be losing temperature. So this delta T is negative 50C, and it gives off 500 joules. So that is going to be negative 500 joules. Okay, so there's directionality to these. Now let's use our equation, Q equals Sm delta T. Plug in the values that we know. My Q is negative 500 joules, is going to be equal to S, the unknown, times the M, 100 grams, times the delta T, negative 50 degrees Celsius. So in order to solve for S, we'll divide out the 100 and the negative 50 from the 500. I'll go ahead and pull up the calculator, and we will do the math here together. So we have negative 500. I'm going to have to divide away the 100 and also divide the negative 50. And we can't do a minus operator. This is going to be awesome. Okay, instead, here's how this is going to work. Negative 500 over 100. So that is negative 5 divided by, I'm just going to take the 50, and then we'll make that a negative. So it is 0.1. All right, so right here we find that the S is equal to 0.1. And the unit for that is joules per gram degrees Celsius. Now, the next question, how much energy is gained when 200 grams of a liquid sample, so 200 grams, this is a mass, is heated from 15 degrees Celsius to 40 degrees Celsius. So this is the initial T1, and this is T2. If the liquid has a specific heat of 2 joules per gram Celsius, so this is my S. So what I'm going to do here is I'm going to go ahead and first put together my delta T. Again, recall delta T is T2 minus T1. So 40 minus 15, the delta T is 25 degrees Celsius, and that's a positive value. So plugging in Q equals Sm delta T, I'm trying to find out how much energy is gained. So Q is what? And I'll plug in my S, 2.00 joules per gram Celsius, times my mass, 200 grams, times the delta T, 25 Celsius. What we're going to get here is 2 times 2 is 400 times 25 degrees C. So let's do that real quick on here. 400 times 25 gives me 10,000. So the amount of energy gained is equal to 10,000 joules of energy, which could, in more common terms, we typically would convert that to 10 kilojoules of energy. Now, number 3, what is the final temperature of a 10-gram sample of water that begins at a temperature of 60 degrees Celsius? So again, let's go ahead and start these. What is the final temperature? T2 is question mark. Of a 10-gram sample, so mass is given. The water begins at a temperature of 60 Celsius, so this is my T1. if this sample absorbs 418 joules of heat. So that's my Q. Now, this one's a little bit different. What we're asking you to do is see that it is a water sample, and you should know that for water, the S is a given value as 4.18 joules per gram degree C. This is a number that you're going to need to memorize. You should know this number. Okay? So we have 4.18 joules per gram degree C. I have a mass. I have a Q. What's missing in this equation is I don't know the delta T. And what I'm really trying to find is T2. If I solve for the change in temperature, I can then plug that into the delta T equation using T1 and find that T2. So let's go ahead and do that. I'm going to say that 418 joules is equal to 4.18 joules per gram Celsius times a mass of 10 grams times delta T. We'll take 418 divided by 4.18 and divided by 10. Delta T is 10 degrees Celsius. So if T1 is 60, we say that delta T is T2 minus T1. I know that the delta T is 10 degrees C, and that is going to be equal to the final temperature minus 60 degrees C. What I can do is add 60 on both sides, and that'll give me T2. So 10 plus 60 is 70 degrees Celsius. All right, now I'm going to ask that you pause the video again. I'll assume that you've done that, and we can work out these problems now. So we're going to calculate the energy that is required to heat 100 grams of water from 70 to 120 Celsius. And this is a concept that we've discussed, but we're going to have to kind of implement this in a little bit of a different way. So just to kind of start things off, I want to recall this phase change diagram for water. Notice that you can have a rise in temperature, and this would be as heat energy is being added. So what happens here is you're going to have the solid phase up to 0 degrees Celsius, and then you're going to have the melting right here. You'll have the liquid phase, and then at 100 Celsius it breaks into the boiling, the vaporization phase. And after our liquid, we're going to have finally the gas phase up here. So what we need to consider is we're going from 70 Celsius to 120 Celsius. From 70, which is about the liquid phase, to 120. So we're going to have to factor in a phase change as well as our standard increases of temperature. So to begin, we're going to break these down by organizing our information. The first thing is we have a sample that is going to begin as a liquid. So I'm going to draw in a box to help me organize this info. It is a liquid at 70 degrees C, and it's going to be a liquid at 100 degrees C, where it's going to start to phase change. After that point, the next step on our graph here is the phase change. It's going to be a liquid at 100 Celsius, and that's going to become a gas at 100 Celsius. Now the third step, the final phase, is going to be a gas at 100 Celsius, turning into a gas at 120 Celsius. Now by organizing my information into these steps, it actually makes it a little bit easier for me to figure out how to find the energies of each of these steps. The first thing that you see here is the state of matter doesn't change, but the temperature does. My delta T is T2 minus T1. That's 30 Celsius. Here, I don't have a temperature change, but I have a phase change. So going from liquid to a gas, I'm going to have a delta H, liquid to gas, is vaporization. Then here, no phase change, but I have a temperature change. And the delta T is 120 minus 100, gives us 20 degrees C as the change. What we're going to do now is we're going to organize what equations get us where we need to be. Since we have a mass, 100 grams, and we're trying to determine the energy required, Q, first off, we see that Q is equal to Sm delta T if we have a temperature change. If there's no temperature change, then Q is equal to mass times the delta H, and in this case, it's vaporization. And then again, when we have a temperature change, this one would be Q equals Sm delta T. So what we're going to do is we're going to plug in the values as we know them. Now, our S value, if we're talking about liquid state, take a look and find the specific heat of water as a liquid. This is the value that we'll plug in, the specific heat of water as a liquid. So we'll say 4.18 joules per gram degrees Celsius multiplied by 100 grams for a 100 gram water sample, and then multiplied by the delta T we figured out, 30 degrees Celsius. Okay, I'm just going to set this up. We'll do the calculations later. Now, this next Q is going to be the mass, 100 grams, times the heat of vaporization, because that's this process. So the heat of vaporization for water is given right here in joules per gram. So 100 grams times 2,260 joules per gram. And lastly, we're going to take the specific heat of a gas here. So in this case, our specific heat is that of steam, 2.02 joules per gram Celsius. 2.02 joules per gram degrees C times the mass, 100 grams, and times the temperature change, which we figured out here as 20 degrees Celsius. All I have to do at this point is find the Q's and then add them all together. So we'll do the math. Let's go back. When we do the math, we find that this value is 12,540 joules. This value is 226,000 joules. And this value is 4,040 joules. So adding these three values up, we find there are 242,580 joules of energy, or 243 kilojoules if we want to round that. Okay, next, the standard enthalpy of formation of nitrogen monoxide gas, NO, is plus 90 kilojoules per mole according to this reaction. So 1/2 N2 gas plus 1/2 O2 gas goes to NO gas. And we said that the standard enthalpy of formation, so enthalpy of formation is denoted this way. Standard enthalpy of formation gives a degree sign, and we're not going to get into why, but this value was plus 90 kilojoules per mole. So per mole of NO formed. If 270 kilojoules are absorbed as NO is formed, how many moles of NO are produced? All we have to do here is set this up as a conversion where we cancel kilojoules. 270 kilojoules of energy. We want to cancel kilojoules to find the number of moles, so we use our conversion, our enthalpy of formation. It will be 90 kilojoules per 1 mole, so that means we have 3 moles of NO that form.